Hello and welcome to today's session, where we are going to look into first some of the simulation techniques that will be required for analyzing the feedback scheme that we discussed, including the high resistance implementation and the common mode feedback and the differential feedback. So, we have seen that the stability analysis for these circuits is going to play an important role in the overall analysis of the system under consideration, and therefore, I am just going to describe briefly the steps to be followed to implement or to do the stability check for the common mode and differential loops. So, let us get started with the overall feedback scheme that we have and look into both the feedbacks, common mode and differential, and then look into the stability analysis that we are going to do at simulation level. So, theory point of view, we have already discussed how to do the simulation, how to do the stability analysis, but in order to implement that in simulations and verify our concepts that we have learnt in the theory, it will be important to just discuss how we are going to follow these steps in the simulation. So, let me start with a single stage diffamp, where I am trying to compensate it with the help of a common mode feedback error amplifier. So, let me redraw the topologies that we discussed. So, this is our error amplifier, and we have discussed the common mode half circuit, where we need to open the loop. So, here I am drawing current mirror load configuration for the error amplifier, where I have the VO1 and VO2 coming at the inputs, and you have the reference signal over here. And what we discussed was that the output of this error amplifier is fed to the input of the PMOS. Now, in order to open the loop, we can open the loop at several points. One option is that we can disconnect the output of the error amplifier from this PMOS gate, and then we can take this as the input point, keep the connection between VO1, VO2 and the NMOS as it is. So, I will keep this connected, but I will disconnect this one and then apply the signal over here and observe the final output over here. So, that is one way of opening the loop and doing the stability analysis. The other option is that, as we have discussed in the theory session, we can open the loop over here. So, we can disconnect the input of the error amplifier from the two outputs, and then keep the connection between the output of the error amplifier and the PMOS as it is, and then observe the final output coming over here. Under that condition, we said that we will be applying a AC signal over here, and of course, since it is going to be a common mode operation, both the outputs will be changing in the same fashion, and therefore, that behaves as my final output, that is the A beta factor. So, this signal, observing this signal is equivalent to observing the A beta times the input signal. So, these are the two ways in which we can do it. The consideration, however, that we should be aware of is that the DC biasing condition of this particular circuit as well as the error amplifier should remain unchanged, because remember the small signal parameter that we use in the stability analysis, the GM, the RO, etc., that depends upon the DC bias conditions of these transistors, and therefore, the small signal parameters GM, RO should remain constant or same for the open loop as well as closed loop conditions, and that would imply that the DC bias voltages and the currents, especially the currents in the MOSFET, they should remain almost constant, almost same as the closed loop case. And to do that, if we talk about the first case, when we are, for example, opening the loop over here. So, in that case, my VO1 and VO2 is still connected to the input of the error amplifier. These two are anyway set to AC ground or their respective DC bias point. So, if I talk about the exact simulation, of course, whatever DC bias point was applied at these two inputs, we can keep it as it is. So, we can and remember that when we are using the common mode feedback, we had set the output DC point with the help of common mode feedback, while for biasing the input we used a resistive divider over here, large feedback resistor over here, RF from VO1, VO2 to the input devices, and that ensured that the input DC point was equal to the output DC point. While opening the loop, also we can do the same analysis. We can also keep the same RF, because as long as we are ensuring that the VO1, VO2 DC points in the open loop conditions are going to remain same, that will also ensure that the input DC point over here are also same. However, if you look at the input signal over here, that if you are having a overall signal coming over here, it will induce some signal at this point also, unless you have some significant input capacitance placed over here for the for establishing an AC ground. Therefore, in order to ensure that this point is at AC ground, either we need to put an capacitor over here along with the RF, or the other option is that you remove the RF and then apply only ideal DC voltages over here with values equal to the closed loop condition. So, in the closed loop condition, we know that we had put the common mode DC output voltages over here. So, we can just connect DC voltages over here, which was equal to our VOCM under closed loop condition. So, I will put just the same VOCM over here. This is anyway coming from the reference current mirror branch, so I do not need to talk about this. So, this is this may be coming from a reference current mirror branch, and here if I am opening the loop over here, for that I also need to make sure that whatever DC point was available with the help of the error amplifier at this point, the same is maintained. So, before opening the loop, suppose the amplifier give us a voltage of say 1.5 volt DC over here for a 1.8 volt VDD. So, after opening the loop, when we are applying a signal over here, we have to make sure that I apply a same 1.5 volt DC, and on the top of that apply my AC signal V in to check the open loop response, because the DC bias condition must be maintained. So, under closed loop it was giving me 1.5 volt DC, and therefore, after disconnecting also I keep the same 1.5 volt DC, and that will effectively ensure roughly that this VO2 and VO1, the DC common mode, this is also remaining more or less close to the previous value, and therefore, in the open loop simulation, the DC values over here and hence the DC value at the gate of these two split transistors, they will also remain similar. And of course, here we also need to keep the same Vref, I would say VCM ref, that we had under the normal closed loop operation, and then apply an AC signal on the top of that, V test if you call it. So, this is the test signal, the AC signal, sorry, in this case we are not applying the test signal over here, but we just need to put it at the required VCM, because in this particular case, first case, I am assuming that the input signal is applied over here. So, you just need to make sure that this is also at the same VCM ref that you had applied. And one point to note is that this is a high impedance node, and therefore, even a small change in this DC voltage 1.5 volt can result in a significant change in the DC bias over here. So, because if you look at the input point over here with respect to this particular DC plus AC combination, this is acting like a common source amplifier with input as the PMOS, and these are just acting like the load device. So, if you remember our discussion on the open loop analysis, this behaves like a cascode device with the gate as AC ground, and therefore, with respect to the signal over here, the input pair, this acts like a common source amplifier's input pair, and whereas the NMOS transistors over here and the NMOS of the current source acting like the cascode load. Now, if we therefore want to look at the signal over here, a small change in the DC level, even 1 millivolt of change, can produce a large shift in the DC potential over here. So, remember, we are designing this circuit for an overall gain of greater than 10 to the power of 4. The open loop gain of these amplifiers, the two stages overall, can be 10 to the power of 4 or higher, and as a result, each of these stages, the differential stage and after that the common source stage, can have a gain of 10 to the power of 2 or higher. So, few hundreds, it can reach 1000, and as a result, a few millivolt of shift in this 1.5 can also result in a significant shift, hundreds of millivolt shift over here, and therefore, it will be prudent to read these values carefully in the simulation. Also, if you look at the DC value, you have to put very precise values over here, which was same as the value provided by the feedback circuit, and if you are not getting exact same DC potential over here, it is also advisable to sweep this 1.5 volt DC across the mean value. So, you are expecting that the 1.5 volt DC putting over here will give me the right DC potential over here, which was under the closed loop condition. But if it is not coming exactly and you want to be more precise about the DC bias point and make sure that in the open loop condition this DC bias is remaining same or very close to the previous one, you can sweep this DC potential. So, in the simulation analysis you have the option of DC sweep. So, you can select this DC potential and sweep it across 1.5 volt. So, maybe 1.5 you can go from 1.55 to 1.45, and within this range you can take large number of steps, say a few tenths of steps, and see the overall characteristics of the DC point over here. So, if for example, if you do such a DC sweep, so if I call this VGP, if you sweep this VGP from the lower value 1.45 and 1.55, if the value is going up, the output potential will be going down, and whatever point you get the output potential same as the previous value, that is your VCM ref, you can pick up that VGP and put it over here, right. So, you can sweep the VGP, I am calling this the VGP, the DC potential. You can sweep this little bit across the expected value of 1.5, and at whatever point you get the output DC, this is the y axis, I am plotting the VO1 or 2. So, at whatever point the VO1 reaches VCM ref, very close to that, you can pick up that value. So, that will be much more precise. So, you will make sure that the output DC point over here is very close to the required DC point under closed loop condition, and we will also make sure that the DC point over here for these two VO1, VO2 that you are having, that is also close to the closed loop condition, and the GMs etc. are very well matched. So, this is the condition you should just check for while opening the loop, and once you have opened the loop, then of course, you can apply the AC signal over here and then look at the final output coming at this point. So, here I have just tried to complete the analysis from simulation point of view. So, in the real simulation, how you will be doing the analysis to obtain the overall phase margin. And likewise, if you are looking at compensation, so that for the compensation part, once again you are either going to look into the capacitances placed between the output over here and this point, or you can look at the capacitance placed between the output node over here and the output here. And if we look at the overall capacitance coming between, suppose you are putting the capacitance between this point and this point, then of course, the main amplifier also is having the Miller effect, and the overall capacitance over here will be multiplied, whereas for the other node, when you are putting the capacitance, that effect is not coming into picture. So, if you have a cap which is connected between, say, in the compensation scheme, that when you are using a cap between the outputs over here and the output at this point. So, that can lead to Miller multiplication between the caps, between the input stage and the output over here, and but that is however going to load the main amplifier also, which is not very advisable. However, if I am looking at the Miller effect between this point and this point, after opening the loop, we can see that the capacitance will not be coming in the loop simulation, or the open loop simulation, because that is the loop over here has already been broken. So, in order to load this particular point with the capacitor, it will be advisable to put a Miller multiplied capacitance value over here. So, that is one possible solution. So, let me talk about the other scheme, the other alternative that we also need to see. So, some of you who have tried the other way, in which the loop can be opened, say, at this point. So, once again similar considerations. So, if I am opening the loop at the input point, so there also we just need to make sure that the overall DC conditions is maintained. So, under this condition, we know that once again the input point, anyway they are supposed to be at the common mode DC level. So, I will just put the same VCM over here, the DC level expected, and this is the same DC point, and the differential pair or the split pair that you have. We are breaking the loop over here, and therefore, these two DC point, these two gate voltages need to be connected to the common DC point. So, I will connect these two with the same DC level that I was expecting, VCM, and then at the other input, once again I have the VCM ref applied, which is equal to the expected VCM. So, this is the DC potential, and then you apply the V in for testing over here, and then complete the loop. So, in this case, once again we have taken care of the DC biasing. So, the input DC potential over here is maintained, and we are trying to observe the output voltage over here, and as a result we have the overall DC conditions maintained all throughout in the main amplifier as well as in the error amplifier. So, this is the condition you need to check while doing the open loop simulation for the common mode feedback that we have. Likewise, if we do the common mode feedback for the whole two stage, there also similar biasing conditions need to be checked and ensure that the overall error amplifier and the two stages are maintaining the same biasing scheme. And suppose you are using the same single loop for the common mode feedback, then overall it remains, the scheme remains same. Only thing is, after that you will have another two stages added, which are the common source stage, and you are basically trying to, so these are the additional stages which get added, and your output, you are taking it from these 2 points. The other thing that you also need to make sure is that you are checking the polarity of this one. So, some of you have pointed out that when you connected the 2 stages in the loop, this particular scheme was not working, and that is because you have probably not changed the polarity, because for the single stage, if you look at the polarity, this is the correct polarity because it is giving us overall negative feedback. So, you can trace it back and check whenever you have doubt. So, assume that output common mode, just assume that you are just having the single stage. In that case, you are just trying to trace and figure out that yes, this connectivity was correct. To do that, what did we do? If you remember, if you assume that the output common mode voltage has increased because of some reason, and as a result this was connected over here, and therefore, this common mode voltage going up means this voltage going up, and that means the PMOS gate voltage going up, and PMOS gate voltage going up means the VSD must go down, and therefore, VSD must go up. As a result, the drain voltage must go down, and that will again bring my output common mode voltage close to the required value. So, that was the mechanism of negative feedback we discussed. However, if you are having the other stage inserted, then also we need to take care of the polarity in the resulting closed loop, and therefore, now if you see this voltage going up, that would mean that these two outputs over here will be going down. That means the input voltage over here will be going down, and as a result this will be going up, and this will be going down, and I do not want this downgoing voltage to be applied over here. So, rather than that, I would like this particular drain voltage to be applied at this point, and to do that I will make this the output node, and therefore, I will have to connect this, make this diode connected and take the output from here. So, this will be out, and this becomes my new output, this will be also out, and when I am taking the VO1 and VO2 from here, in that case, in order to ensure negative feedback across the loop, I have to change the polarity of the diode connection. Output has to be taken from here, and then we can once again follow the loop and make sure that yes, you have overall negative feedback in the common mode loop. This voltage going up means output of these two common sources going down. That means the input of these two NMOS transistors going down. That means this voltage going up, and that going up means once again it will help in bringing these two voltages down. So, that is supposed to be the case. So, you just take care of the right polarity if you are using the same single loop for the overall common mode feedback. However, if you are using two loops, like for the first stage a separate loop and the second stage a separate loop, then the polarity remains same, and that is something you should be aware of. And in this case, if you are using two stages, and there also ultimately when you open the loop using the second scheme that we discussed, you would like to maintain the output common mode at the same point, and in that case it may become a little bit more challenging because the gain from here to here is large, and you are applying a signal over here, and you want to make sure that the output DC point over here is close to the common mode point that you expect, and therefore the sweeping scheme that I discussed, that becomes all the more important, because you do not need to be precise, you need to precisely locate which point you want to have at the biasing the DC bias, so that the output DC levels over here obtained for the closed loop operation, they are very close to the common mode voltage that was obtained using closed loop. In the single stage gain, you had the gain from the gate of the PMOS to the output given by GM RO by 2 or GM RO precisely, and however, in this case the gain from here to here is further larger, GM RO square. Therefore, a little bit of change in the DC potentials here can change the output DC point significantly. Therefore, if you want to ensure that the output DC point should be very close to the desired value in the closed loop, you just whatever DC you are applying at this point, for example, you can sweep it a little bit across the ideal red value, and that will ensure that you are able to find out the right precise value of the DC, so that this point is at the required value.
So, in the error amplifier, for the first part where we are giving input to the two gates, we want them to be equal to the output of the common source amplifier, right?
Yes.
So, we want the output of the common source amplifier to be close to VCM ref, right? So, why are we giving VCM? We should give VCM ref.
That is VCM ref, means VCM ref, that is the expected value. Only thing is that little bit of change, if you are not giving it very precisely, the output can swing by a large fraction. So, in the feedback loop there is a negative feedback, and it will try to adjust with little bit maybe by a few millivolts or fraction of millivolts, so that the output is coming close to the desired value. When you open the loop, that negative feedback or the stabilization effect is removed. Therefore, the required value over here to achieve the same voltage may be slightly different. So, it may not be exactly same. So, for that you need to just do this sweep in the open loop case, so that the output point is coming close to the desired value. In the negative feedback, means eventually it will not be exactly same. So, it will have some error, because remember in the negative feedback, what do we assume? If there is an error amplifier, we assume that once you connect it in negative feedback, these two are exactly same, but that does not happen, because if there is a finite gain amplifier, there will be some minute difference between these two inputs, and that is ensured by the negative feedback. Therefore, either you have to read the voltages very carefully. In simulators it may not show all the decimal places. So, in that case, if you want to get the precise value, you are having the negative feedback and you want to get the precise value of the DC potential over here, you need to basically do the sweep as we suggested over here. So, rather than choosing the exact VCM ref, you need to sweep it a little bit and then find out the exact VGP in this case, for example, to get the exact right value of the output voltage. And likewise, in this case, when you are opening the loop here, you need to maybe sweep this particular DC voltage, so that the output potential over here is equal to the required Vref. What I am just trying to point out, that if you just simply open the loop, it is not necessary that under the open loop, if you apply this VCM ref over here and the same VCM over here, it is not necessary that you will get the same value VCM over here like you were getting in the closed loop. Why? Because in the closed loop condition, the amplifier finite gain of the amplifier will ensure some minute difference between the effective common mode coming over here and the common mode that you are expecting over here. And when you open the loop, that mechanism is not present. So, you need to make sure by sweeping this value little bit, so that the output DC potential over here is equal to the required common mode. Because remember, the gain from this input point to the final output is going to be pretty large, GMRO cube, and as a result a little bit change over here can produce large changes in the output DC potential, and therefore just to ensure that the output DC potential is close to the VCM ref, it is not, it doesn't have to be very exactly close, 0.1 millivolt close, but at least few millivolt, within few millivolt different should be close, so that you are getting accurate common mode accurate open loop analysis.
So why to add the compensation capacity?
So as we have said, in this case we have a fight between the differential operation and the common mode operation. So if you try to add capacitor between the output of this one and the output of the error amplifier, so that does have the mirror effect coming over here, but it also has mirror effect coming over here. So we discussed how to isolate that. You insert a buffer and then use that. So that will basically introduce Miller effect here strongly. So that will try to have a large compensation, effective Miller multiplied capacitance over here, but you don't want that Miller multiplied capacitance over here, because in the closed loop, if you see that capacitance also comes between this point and this point, we are having a signal path from here. So we discussed that, okay, let us have a buffer and then connect the capacitor between this point and the buffer output at the first stage, so that the buffer output is having low impedance. Even if there is a Miller effect coming over there, it will not affect. So ultimately it is, if you are having a buffer after this for the compensation path between the buffer output and this point, you can put the capacitor. So that
Another pole due to the CH.
no, that is in case you are using single loop. So in the single loop, if you are using this entire common mode feedback, then I suggested that to keep the loop gain within bound, let us have both the PMOS diode connected, so that the loop gain is within limit GMRO square, it is not going to GMRO cube, because in this loop, if it goes, if the gain goes to GMRO cube, all the three nodes that you are having in the loop, they are having equal or equivalent open loop pole values. So if I look at the original case where I am having the current mirror load, you should be able to distinguish between these three terminologies. Current mirror load means only one side diode connected, diode connected load means both side diode connected, and current source load like this is the current source load where none of the sides are diode connected. So when I say current mirror load, that means only one side is diode connected, other side is not having diode connection. So if I use the current mirror load for the common mode feedback for the two stages together, then the closed loop, the loop gain is pretty large, so it is GMRO cube, and it may lead to more instability. Therefore, and the other serious issue is that all these three nodes, the output of the first stage, second stage, and the common mode output, they are almost having similar magnitude of the pole. So compensation becomes a little bit more challenging. Therefore, it may be advisable to use diode connected load for the error amplifier. So in that case, the error amplifier gain becomes smaller, close to 1, because once you do the diode connection on both sides, means you disconnect this gate and do the diode connection on both sides, then the gain of this error amplifier becomes GM1, GM of the input pair divided by GM of the load pair. Just like the differential half circuit, you have a diode connected load. So if you have both of these diode connected, this center connection removed and both of them diode connected, that means the gain becomes GM1 upon GM2, GM of this device divided by GM of this device, and almost close to 1. And in that case, the loop gain will be of the order of GMRO square, so it will be a little bit easier to compensate. And in that case, what we have seen is that you can add a compensation capacitor right over here, as we do it for the differential case. So if you add a compensation capacitor over here for the overall two stages, then anyway you are having the overall one of the poles in the loop becoming dominated, and the error amplifier in that case is not having a dominant pole, because you have diode connected both of them. As a result, the impedance at these 2 points drops, it is close to 1 upon GM. As a result, this is not going to interfere too much with your pole compensation. So in that case, the dominant poles are in the main amplifier only, and this is the output of the first stage and output of the second stage. And then whatever compensation we discussed for the differential scheme applies here also. So there we are trying to compensate the it basically implies that we are trying to have the similar compensation for differential as well as common mode loop also, because once you put cap here, then it also compensates the differential operation, and at the same time it also compensates the common mode operation. Then resume with the rest of the discussion.
Okay.